So the formula for this one is F. This one, what is F? What is your force?
525 Newton.
Okay, remember to change to Newton, huh? Because kilogram is not force, huh? Kilogram is a mass. You need to change to weight. Okay, you need to change to weight. F equal to mg because it's hanging. So gravitational force pulling. For this module, all the gravitational force we use 9.81. So you calculate lah, force divided by area, pi r square or pi d square over 4.
Because they asking for diameter bar. Means not.
Bar is a long shape of, it's a long shape. It's, in this case, it's diameter. Bar can be square shape but long. It can be cylinder also. But here it gives you diameter, so this case lah. Round shape, if you're given diameter. If the question give you square shape with side dimension, then is a square shape lah. Okay. So the answer will be 200 megapascal. So earlier your answer is 1.99. I don't know, somehow you need to fix your decimal place, your 10 power something. This one is in cm, not in mm. Huh? Just now your calculation, maybe you this one 10 power 3. The question give you cm, not mm. Right? So check your careless mistakes. Huh? Sometimes we will not give you the direct forces. We will give you something like example 3, give you the mass in kilogram, and give you diameter or size in cm. So you need to convert to unit SI. Huh? Next, we learn about strain. Strain as a deformation. So if you pull the metals at a certain forces, in this case, uniaxial means one direction, one direction force. You will get engineering strain, give you the change of length divided by original length. Engineering strain, change of length divided by original length, or L sub O. And if you will see the normal strain, mean the direction of force is perpendicular to the cross-section area. Oh, yeah, okay. And normally, the stress and strain will go at the same time. It will happen at the same time. Huh? If you have stress, mean you will have strain for metals. Remember, strain don't have unit. Huh? Non-dimensionless or non-dimension. Why non-dimension? You take change of length is meter. The original length also meter. You cancel the dimension. But you can still write meter over meter if you want. If you're in the dimension, there's one chapter, not in this one. If you study mathematics or study finite element analysis, one process is called dimension analysis. You need to find the final unit of that calculation. Right. So for this module, strain is dimensionless because it's cancel the meter. Usually, when you work in the industry, in the handbook, like what is the maximum strain that allowed in the process, they will write in percentage of strain. Percentage of strain, you just take the strain multiplied by 100%. Strain is a ratio. When you multiply by 100%, you get percentage. Okay. So there are two formulas that you learn today: normal stress and normal strain. These two, you link stress and strain by one formula. Stress equal to E strain. E is the elastic modulus, or we call it Young modulus. Stress equal to E strain. This is called Hooke's law. You will need to apply this one in your lab report. You need to apply this one, explain what is Hooke's law in your lab report. There are lots of names given by the E. E usually in the gigapascal unit. Giga is 10 power. Giga is 10 power how many? 9. Huh? So modulus of elastic or Young modulus. There are two names for the capital E. Right? So earlier I plot a graph with straight line, right? Stress versus strain. This straight line on the stress versus strain, you know that this is straight line that you can write in mathematics, y equal to mx plus c. How you calculate your m, your gradient? m equal to y2 minus y1, x2 minus x1, or change of y, change of x. In this case, what is your y? Stress. What is your x? Strain. So your m, by looking at the slide, what is your m? Is your E. So you rewrite this one into Hooke's law. You get stress equal to E strain. Okay, so in your experiment, you are given a specimen, you pull, you measure, you pull, you measure. So if you're given a rod like that, you pull, you look at the gauge, how many Newton, then you measure what is the length, what you pull, you get the gauge, you measure the length, you let go. Right. Initial length, you pull, final length, you measure. Right. So if you go back to original length, it means it's still within the elastic region. Recall just now, how many deformation you have? You have two types, elastic deformation and plastic deformation. Elastic means what? You go back to the original length or shape after you remove the loading or force. Okay, so this is important. You will see this one in your assessment. Right? Okay. The question won't say Hooke's law. The question will give you all the force and the behavior, like example number 4. Sometimes diagram will not be given. You will see a paragraph of statement. For example, aluminium with you see this one, 12.7 mm wide, and thickness is given, the length is given. Now this one is a square shape cross section or rectangular shape cross section. If you're given wide, thick, and long, okay, you have 12.7 wide, 12.7 wide, and thickness is 1 point something mm, and 203 something mm long. Okay. That had gauge marking to 50.8 mm apart, which means this is the original length. If you see the word gauge length in the question, this is mean original length. The gauge length, the word here is to give you calculation for strain. What is strain? Change of length divided by original length. You need to use the gauge length to find strain. So calculate the normal engineering strain and the percentage of engineering strain that the sample undergo. So how do you do this one? Based on your understanding in the definition just now. So you learn about Hooke's law. What is Hooke's law? Hooke's law equal to stress E strain. I remember by the shape lah. The E and the strain almost same. What is stress? Force by area, but it's a normal direction. Equal to E is the modulus Young. In this case, what is strength? Strength is the change of length and original length. In this case, the question asks you this component. So strength equal to delta L divided by original length. So what is the answer? It asks you strain. What do you take? How many change the length? Again, what you're focusing on? You're focusing on the gauge length, not the total length, not this 8-inch thing. You're focusing on this area, not the total length of the sample. So you take what? You take 2.65 minus 2 divided by 2. Because the formula for strain is change of length divided by original length. What is the original length? Original length is 2 inch or 50.8 mm.
0.325.
Answer is? Sorry?
0.325.
325. Okay, we use mm. We use mm. We use mm. Or you straight away yeah lah. It's safe to use a meter. But in this case, you know, strain is dimensionless. So the unit doesn't matter. So what is the strain for this case? What is the strain? What is the change of length? Change of length is what? 50.8 minus 64.31 minus 50.8 divided by 50.8. So what do you get? 0.325. This is the strain. Percentage will be 32.5%. Okay. So this is the answer lah. The strain will be 0.325. Percentage is times 100. You get 32.5%. Engineering strain or normal strain. In this case, if you're not given the force, you're not able to find the stress. Stress, you need force. Okay. But if the question give you more information. If you're given the stress value, he asks you how many force that generate the deformation. You can find, huh? So this is a strain. So if the second question B section, it give you, if you're given that the same elongation happen and the normal stress maybe 100 Newton, kilonewton, right? So what is the force applied? So you should able to extract from this equation. Any questions so far for the stress and strain? Any question? Now we go into something called Poisson ratio. What I mean by Poisson ratio? Given by this V, weird shape of V, we call it Poisson ratio. So imagine you have an object like you see on the screen here. You pull with the tensile loading. The dot shape is the original shape. If you pull, the side will become thinner, right? It become long and the side will become smaller. So what is Poisson ratio for this object? A tensile stress in Z direction, in this case you have a XYZ direction. Z is going up and down. So tensile stress in this case is the force divided by area of this cross section, right? So you will create normal strain, tensile strain, means this stress pull, it will longitudinal will change, right? This is longitudinal direction, longitudinal, right? So we change means the length will change. We change length, it involves strain. Strain is the change of length divided by original length. You also create lateral normal compression stress strain. What mean by lateral normal direction? I draw something on the board here. When you pull both ends, this is called longitudinal direction. Direction that go perpendicular 90 degree to the normal. These two direction is called lateral. Okay, lateral direction. So if I take the cross-section area, let's say I label A, B, C, D. I draw on the board. This is A, B, C, D cross-section. Longitudinal is at the center that come out from the whiteboard. Lateral, you have two lateral direction. Can you see? Yeah, lateral one, lateral two. So if I put inside my axis, right? So this is Z, this is maybe I follow that one, X or Y. So this is your X, this is your Y. So if you pull, this shape will string, right? If you pull this one, the shape will change, right? The ABCD shape will string, right? Right. So there is a change of length in Y, and there's a change of length in X. So you have a positive strain if you pull normal, means the length is positive, the positive change. but you have a negative strain in X direction and Y direction because it's string inside. Okay, it's string inside on the X direction, with this X direction is this way, so both sides was shrinking. Y direction also string. So you have two set of negative, one set of positive for string. This is a realistic case, realistic case. So there's one more technical word called isotropic. Isotropic, iso means equal. Isotropic means equal change of behavior. All sides you have same behavior. So your EY and EX will same. Means you are dealing with the same material. So take note on the isotropic. Isotropic. This word, isotropic means your elongation or deformation at your X and Y will be the same. This word will appear in your assessment. Okay, so meaning you only need to find one of the elongation or deformation, either in X or Y direction, then it will equal to another one. Okay, this is X and Y only, means the side of the object, but the longitudinal doesn't change. We have two technical words here. One is longitudinal, one is lateral. Longitudinal is along the length of the object, you can say. Lateral is at the plane of the body or the cross section of the body. You deal with longitudinal and lateral when you go into composite material. So there's a definition of isotropic on the bottom of the screen that you can read. We want to find the ratio of your lateral and longitudinal. We calculate with Poisson ratio equal to negative lateral strain divided by elongation strain. The top is lateral, so Poisson ratio equal to minus E lateral and longitudinal. Why there's a minus there? Or minus? What mean by opposite direction? Okay. Why negative? Why Poisson ratio negative? When you apply force, does the strain in X or Y or Z, they are same direction? Same direction means positive value or negative value. Understand? In this case, you get negative because if you pull longitudinal, your longitudinal will be positive. But what happened to your lateral strain? Your lateral strain is negative because it's stringing. This is realistic material. So that's why you have a negative Poisson ratio value there. What happens if you have a positive Poisson ratio? What does it mean? When you apply force, if you have a positive Poisson ratio, what does it mean? You're in a degree, so you have to be sensitive to positive negative sign. You have a Poisson ratio positive value. What does it mean? Strain length and long. What happens? If you pull this object with the positive Poisson ratio, what does it mean? The length change, but the body become bigger and bigger. It doesn't make sense. unless you are creating a new material, or we call it a non-conventional smart material. You pull and then the body grow, something wrong with the properties lah, or something that added to the properties. Okay, another one. Poisson ratio, you can refer to lateral. Lateral, you have two. One is X, one is Y. You compare to the longitudinal. Longitudinal, you only have one. So that's why you can calculate two. And why I can write equal? Because we are having isotropic material. If the question do not mention, if question mention non-isotropic, you cannot equal. You have to calculate one set for X, one X for Y, if the material is non-isotropic. Okay. So for isotropic, you can link what you learn, Poisson ratio, modulus Young just now, and Poisson ratio with this equation. E equal 2G 1 plus Poisson ratio. It's a standard equation which is very, very useful in your assessment. Because E you can calculate, or sometimes you're given. This one you can calculate, the Poisson ratio you can calculate from the strain value. G will be the one maybe missing. Or if you're given G, you can reverse calculate by using Poisson ratio, calculate back the modulus Young. Modulus Young, you can go back and calculate the stress, because stress equal to modulus Young and the strain. So this equation will reverse back all the calculation back to the fundamental stress equal to E strain. So this is important, and this one also important. What is okay? Okay. In this module, especially want to come to final exam, you will see a lot of table at the back of the question. So sometimes we won't give you the E value, we won't give you the Poisson ratio value. In the question, we'll only give you the name of the material. So don't say, don't ask the invigilator, say, sir, I don't have this value, I cannot do. Always check the question at the back, always have table, right? So for this case, you see this table, you have aluminum, alloy, copper, you have E modulus or modulus elastic or Young modulus, and you have two value there. One is in PSI, one is bracket. Use the bracket for this module, because you're using unit SI. You're not using unit imperial. Use gigapascal in your calculation. All right. You have shear modulus, you have Poisson ratio. Same, another table also. So you have modulus of elasticity, shear modulus, Poisson ratio. And this is a graph form. This is modulus elasticity on the Y, temperature, and modulus of elasticity on the Y another side. What is the difference between left hand side, right hand side? Left hand side is gigapascal, which is normally we will use, and right hand side is gigapascal, just to balance the gigaforce and the imperial unit. Normally we will use elastic. So in assessment, don't panic if you see two axes with the left hand side and right hand side same unit. It just give you like a ruler that you can draw a parallel line from the left to right. So you can capture the perfect horizontal line. Okay, same with the top and bottom. So this one is Celsius at the bottom, top is Fahrenheit. In assessment, sometimes you see 2 Celsius and top and bottom. The purpose is to give you draw a vertical line. You draw the top and bottom, then you get the intersection. You get the exact point. You'll see that one when you look at a phrase table in chapter 7. Okay, so you have tungsten, steel, and aluminium. Modulus of elasticity, aluminum is lower compared to tungsten. For example, how you use this table, or how we ask you in the assessment if you see this table. Right. So I'm drawing something on the board here. If the question give you something like determine the elongation of aluminum and maybe tungsten under force of maybe 100 kilonewton by referring to this table, right? So in this table, at 200 Celsius. So you're given this statement, find elongation of aluminum and tungsten under force of 100 kilonewton at 200 degrees C. By looking at this chart on the screen here, how you do? You draw temperature up. Not straight lah, but roughly, it goes up. You get aluminium modulus elastic. So here is about maybe 70, maybe lah. So tungsten, although it's not straight line, so maybe 400 lah, maybe. Okay, the unit is gigapascal. So from the graph, you have E aluminium and E tungsten. E aluminium 70 gigapascal. Tungsten will be 400 gigapascal. We have E, call out the Hooke's law. The next steps are normally Hooke's law. You write in the answer, Hooke's law equal E, stress equal to force divided, not this one, E strain. Then write what is stress change L over LO. So it depends on the question whether he asks you on what. So of course this one will give you the dimension of the thing lah. So let's say you have 1 meter cross section. So A is 1. So force you have. Modulus Young you have from the graph. So the original length maybe here. I give you original length maybe 1 meter also. So you can find the change of length for aluminum and tungsten from the graph. Make sense? Does it make sense to you? Right. So these are important when you come into your design, your product design module later. When you come to your final year subject, or you do your final year projects, you need to verify. You need to explain the value that you use in your calculation. So you need to refer to a material chart and so on. Okay, so I already teach you how to calculate earlier. So when you come to your final year, don't say, Dr. Ang, I don't know this one. Because high chance I will be your panel of for your Viva, for your final year projects presenter, assessor. All right. Few more slides, then we stop now. Okay, so now we go into shear stress. Don't confuse between shear and stress. Shear, it just tell you the direction of the force. Stress is stress. Stress is force divided by area. Shear is just tell you what is the direction of the force that you need to pay attention to. Okay, don't confuse yourself with the shear and stress. They are different things. And here is stress is not force. Shear can be shear force. It can be shear loading. So shear is just tell you the direction of the force with the cross-section area. So if you see the word shear means it go parallel with the cross-section area of your interest. Stress is mean force divided by area. Stress is means you take the force that parallel to the surface divided by the cross-section area. So if you see on the screen here, on the cube body, and you see the arrow, right? The blue arrow, we have 4 blue arrow there. On the top is to the right, at the bottom is to the left. This is called couplet. We call it couplet force. How to spell couplet? C-O-U-P-L-E-D. Couplet means it go in pair to balance the force inside the plane. But you learn static equilibrium. If not, then the cube will be turning. So we don't want the cube returning to be stable equilibrium. So top will be balanced to bottom, left will balance to the right, same. We're observing the direction of the force is go parallel to the surface. That's why we are looking at shear force or shear stress. Combination between the shear force and the surface area, it will give you shear stress. Okay, so this shear stress, you try to remember, imagine this one as a rubber material. If this one was stick to the surface and there's a force that push to the right, there's a deformation, angle deformation from the origin to the second position with the theta change of angle there. Okay, and then there's a distance traveled from the top surface A here at the edge here. So original and it give you an angle. And there's a H there, the H sample height. So this one also you can give you one calculation, right? It give you shear stress. Again, you take what is stress, force divided by area. What is shear? Shear means you focus on the force that go parallel to the area. Like what I draw on the whiteboard just now. Right? Same force, but it'll give you normal force and shear force. So look carefully. Look carefully. The force must be, if it's shear means it focus on that particular surface cross-section area. Okay? You look at the force. What are the force touching? Okay. Same, the unit will be force is in Newton, area is in meter square. What I need to highlight is the direction of the force acting on the object. Then it gives you one more technical word. It's called shear strain. Give you gamma. The shape, the symbol is gamma. It gives you A divided by H. Again, you look at the word strain. What I mean by strain is a deformation. Means there's a change of shape or there's a change of length. In this case, you take A divided by H. Because it's a shear. Shear, again, shear is deal with the direction of the force to the cross-section area. So you take A divided by H. And if you look at this diagram, you see the angle, right? Angle is here. Do you see a right angle triangular here? Recall trigonometry. What is tangent? Theta. Tangent theta equal to opposite and side. So A divided by H also give you tangent theta. Make sense? Okay. It's a trigonometry application. So if you have pure elastic shear, again, What is elastic mean? It can go back to its original shape or position after you remove the forces or loading. It will give you this equation, which is shear and stress. So G is the elastic modulus. G is the elastic modulus. Gamma is the shear strain. And this one, tau, this one is the stress, shear stress. You have a shear stress, right? This is a shear stress. This is a shear strain. Okay, so just now you have stress over E strain. This is a normal component. But if there's a shear, then we use another symbol, which is shear stress, also stress, but is in the shear direction. This gives you shear modulus. This G is elastic. G is the elastic modulus, which is in the table. Just now I flip back. This modulus elastic is E. This shear modulus is G. This gives you find normal direction force. This will give you find shear direction force. Okay. Typo error, I think just now. This is, should be shear. It's not elastic modulus. You can say it's elastic, but it's in the, you can say shear elastic modulus. Okay. Okay, last example. Example 5, then we call it day. So you're given 305 long, pull in a tension. Tension means both direction. Both end in a longitudinal direction with a stress megapascal. If deformation entirely elastic, I give you elastic. So elastic means you can use either a normal stress equal to E strain or shear. Shear stress equal to shear elastic and shear strain. In this case, it asks you the resultant elongation. In this case, what information you have? You have original length, you have the stress. It asks you what is the resultant elongation. Okay. So in this case, we start with two equations, stress and strain in normal direction. Then call out the Hooke's law. You rewrite the equation. Right? You rewrite the equation. You want to find the elongation, right? So you pull this one to the left, pull this one to the left. You get the one on the right here. Then you go to the table just now. This is how you apply the table in your assessment answer question paper. You see this table, you have modulus, elastic, and shear modulus. This formula is under modulus of elasticity, and this one is under copper. So this again, we are using unit SI. So we're using on the left-hand side gigapascal here. So we are using stress is given 276 megapascal, so power 6. Original length is 305. E is 110 gigapascal, 10 power 9. Try to observe how you apply the table, how you apply the Hooke's law. In this case, why you do not use the shear equation? Because the question do not give you the exact information. You do not mention shear or do not mention parallel. Okay, so you get 0.77 mm. Okay, we stop at example 5. We continue in our next lecture.